He is going to talk about stabilization of a logical grid state qubit by laser cooling. So, Jonathan, it's your stage.
Great, thanks. Sure, but this morning it was just showing. So. Okay, good, so you can hear me. So, along with the other speakers, I'd like to thank the organizers for their persistence in following up with 2 years of ICAP, and thanks for having us all here for this nice conference. The purpose of my talk today is to tell you a little bit about some of the work we've been doing with a single trapped ion in my group on trying to perform quantum error correction in the motion of a single trapped ion, which is considered as a single oscillator. So this follows up from the sort of phase space diagrams, and you've seen some of these from Klaus Mollmann just now, that you see of these quantum states are here. This would be position of our ion, this would be momentum of our ion. And what I want to show you today is how we use these states to perform error correction and indeed can extend the lifetime of a logical qubit in this system. So the work is experimental work. It was primarily carried out by Brennan and Van Long, and Tanya is also heavily involved in this experiment. So, where do we come from in this? Quantum error correction is a kind of key bridge, if you like, from going from small-scale quantum systems, which I think we all have in our laboratories today, but which are faulty, and getting to a full-scale quantum device, which is large enough to do useful calculations. It's really the essential point. But it's also a beautiful piece of physics. In fact, when I got into my PhD, I worked with Andrew Steen, who's one of the founders of quantum error correction, and I've always found this beautiful. I never thought we would be doing it, and somehow it's wonderful that we are finally doing it. And in a multitude of labs these days, you now see results coming out on quantum error correction. So, what's the way that we can try and protect these fragile quantum systems from interactions with their environment? There are a couple of key principles that are in play, and the first of them is really to say errors should look different from how you encode and manipulate logic. And so, for instance, if you have errors that act locally on a system, well, you should encode your information across a very large degree of freedom, an entangled degree of freedom of many systems. But the other thing you have to be able to do is be able to go and interrogate the system and see if errors happen, such that you can perform feedback in order to stabilize the system and preserve the precious information. And so quantum error correction, as it started initially, was all in terms of how do I do this in the context of qubits, so two-state systems, such as the internal pairs of levels of a single trapped ion. And there, as I've sort of indicated, the information gets stored in non-local entangled states, but in a more quantum mechanical way of looking at things, the fact that you have a lot of qubits all together gives you a big Hilbert space, and this is redundant. It's got much more space than you need to store just one qubit of information. And so what challenges does that provide when we start to try and build these systems, and why did I make this comment that I always thought it was going to be very hard to do? Well, the deal is that even a minimal instance of quantum error correction consists of something of the order of 7 ions to store the information, or 7 qubits, plus many to perform proper error correction on this system. And this always looked challenging, albeit that in Reiner's group and in other groups around the world in the last few years, people have performed staggering experiments to get these things actually to work. But there's another way that you can do error correction, at least at the lowest level of your system, and that's to make use of other types of physical systems that have redundant Hilbert spaces, have a Hilbert space that's much bigger than the Hilbert space that you need a two-state Hilbert space of a single qubit. And that's what I'm going to tell you about today. That's these bosonic codes. In particular, here we're talking about oscillator codes. And an oscillator, of course, has an infinite number of levels, very large Hilbert space. And if we can control it in the right way, we can still store and manipulate qubits in a redundant way to allow us to do quantum error correction. So this talk is really then about a single oscillator storing the information with a single two-level system used as an ancilla to control that oscillator. Now, I should just say that bosonic codes are not the complete path to quantum computing, okay? They basically will be a lowest level error correction that can be used to suppress errors at a single physical system level, and then they have to be concatenated into these much bigger codes in order to build a quantum computer. So they don't make this redundant, but they're certainly a simple way to access principles of error correction, and I think the physics is very nice. So, what is my spin and oscillator? I work with trapped ions. So these are electrically trapped charged particles. They sit at their equilibrium position and they vibrate about them, and that's a center of mass oscillation. And they have internal degrees of freedom, electronic degrees of freedom that are highly anharmonic and give us two-level systems that we can couple to the two with laser light. And this whole talk is going to be about a particular Hamiltonian that we can realize if we look at the spectrum of a single ion. So what we would see if we scanned a laser across this system, we would see a transition where we drive the qubit, but also phase modulation sidebands, essentially, where we have the light being modulated by the motion of the atom. And this talk will be about a particular Hamiltonian where we drive simultaneously at both of these modulation sidebands with a bichromatic field. And that produces a force, i.e. a term in a Hamiltonian that's proportional to the position, Q, which is dependent on the internal electronic state of the atom. And it's a common Hamiltonian for us. It's used in all the Malmer-Sorensen gates that people use in entangling systems in trapped ions. So what's the action of this sort of Hamiltonian on a simple motional system and spin system? Let's imagine that the spin was pointing up, so it's up along the Bloch sphere. What this looks like, if you look at the spin operator here, is a rotation of the spin. And it's a rotation that's proportional to the position and proportional to this alpha parameter that we can control, which is the amount of time we actually apply the pulse for. So this leads to a rotation, and now we can think about measuring the spin, and what are the outcomes of the measurements? Well, they're projections back onto the different axes. So in this case, what do we have? Well, if we measure in the z basis, we get a cosine projection of this angle back onto the basis. And if we measure along the y-axis, we get the sine, okay? So by making a spin measurement, we get an outcome for the spin measurement that's proportional to some expectation value controlled by the motional state of our oscillator. And indeed, it's this modular function, cos or sine, of the position of the oscillator in this case. So let me show you how that works and just convince you of that. Here are two squeeze states that we produced in the lab, right? One of them you see is at position 0. The other one's at position a bit further away from 0. And now we perform such a measurement, and we're going to look at this cosine and sine. And of course, if I have something at position 0, then cosine is just not oscillating at all, and sine will be 0. And you roughly see that, but you do see that at larger values of alpha, we don't see any signal. I'll come back to that point in a moment. If we look at the displaced state, right, then what do we see? We see that when we look at the cosine, well, it's peaked at 0, but it oscillates as we go away from the origin, right? So this oscillation is telling us how far displaced was our original state from the q equal to 0 point. And for sine, we see exactly what we'd expect as well. Now, why do these signals not just oscillate, right? Well, that's because of an effect which is due to entanglement between the spin and the oscillator. So while we're making these measurements, what we're doing is also acting on the position, or on the momentum, actually, of the atom. So this operator here can also be seen as a displacement or a drive along the momentum axis, yeah? Now proportional to, and I apologize, I've changed notation, the capital X is now the sigma X operator from before. So what's happening there is that we're taking two copies of the state, and depending on whether we're in the plus or minus X eigenstate, we're pulling them apart. And as we pull them apart, they stop overlapping, and when they stop overlapping, we stop seeing the oscillation of this rotation of the qubit. And that's what's happening at the larger values that we get here. That's going to be relevant in a moment. So now what I want to tell you about is how we use the sign behavior of one of these components in order to do laser cooling of our oscillator. So the circuit actually is something that came up recently from Michel Deveray's group working on superconducting qubits, and where they were actually performing error correction similar to what I'm going to show you later. And the circuit looks something like this. It's got a coupling, which is exactly the one I've just described to you, and followed by that, there's a measurement in the y basis, so this is this sine component, and feedback on the state of the oscillator. So what I want you to consider is a Bayesian picture. I'm going to describe to you a Bayesian picture of how this produces cooling. Imagine that you have a Gaussian wave packet, that's the gray here, and now we ask what are the probabilities of getting y up or down, and both of these probabilities will be conditional on the position, and it's conditional like the sign of this 2 alpha times q. So now what we can say is if we were to measure spin plus y, then we should update we also have a back projection on the motional distribution, and the probability distribution by Bayes' rule will be updated by this conditional probability. So what do we get? If we had plus y, we would get a new distribution looking like this red curve. If we had measured minus y, we should expect the blue curve here. Now, with the settings that I've used, one thing you'll notice about those two curves is they both look like Gaussians again, right? But they look like displaced Gaussians. And this gives you the indication that if you now record that measurement result, you can push these Gaussians back to the origins, and you should get a new Gaussian distribution. And indeed, that's what happens. And what you see is that this Gaussian distribution is narrower than we had before, right? And in laser cooling, that's exactly what you want. You want to take some broadened distribution, and you want to push it together. So that's actually something that we've used for laser cooling. So we don't actually do the measurement, right? Actually, we can do this conditional feedback just with a unitary pulse followed by optical pumping of our spin, exactly as you would have in standard laser cooling. And then with a combination of doing a measurement and correction on the position basis and a measurement connection on the momentum basis, we're able to suck out or continually narrow down the Gaussian distributions that we have. And it's got an interesting feature. The interesting feature is that on every pair of cycles, we remove a constant fraction of the energy of the oscillator. And we're actually quite efficient. So one fundamental limit you could think about how you can suck entropy out of this system is that you have to reset a spin twice. And so you can get basically 2 kb log 2 of entropy out of the system, which would reduce the motional energy by a factor of 4. In our case, we don't get to a factor of 4, right? We get a factor of 1 over 0.6, but still we're within a factor of a few, actually, of a very, very fundamental limit, I would say. So it's interesting that this picture leads to quite efficient cooling. Okay, so how does that relate to this error correction code? Now I have to describe to you the error correction code. This is a beautiful idea that comes from Gottesman, Kitaev, and Preskill around 2000 and wasn't realized for many years, but it's actually linked to some nice ideas that I've played around with in John von Neumann's work on quantum mechanics. So the basic idea is you try and construct a qubit. So what do you need? You need a set of operators, which are your Pauli operators, which generate the algebra of your qubit, right? So these should anti-commute. And in addition to that, you would like to have, for an error correction code, you'd like to be able to measure the system, obtain information about errors without disturbing the logical information. So you need another set of operators which are going to commute with all these logical operators. And in this code, all of these come from displacement operators. And they come from a fact that when you reverse the order of two displacement operators, you have to pick up a geometric phase, essentially. So this phase is proportional to the area, and what it means is for two discrete displacements of a given length, then we can, if we choose the length of those displacements, we can choose the phase factor that turns up here. And so we can choose if this product is odd multiple of pi, they anti-commute. If it's an even multiple, they commute. So what does that mean? Well, it means that we can define operators, displacement directions, and magnitudes which anti-commute, and we can define ones which also commute with all of those. Yeah? And you'll notice that all of these are exponentials. They're all displacement operators. Okay? So we need to be able to measure and control displacement operators if we're going to deal with these codes. So what does the underlying quantum state of these codes look like? Well, in a theory proposal, you would say, okay, it's a regularly spaced array of delta functions. You have to have eigenstates of these discrete displacements in phase space. So here would be a 0 state, okay, and it's displaced. This is the distance of the stabilizer, which is basically how often these code states have to repeat, and it's a set of delta functions here. The 1 state has to be distinct, and it's separated by exactly half that distance, and that's the logical operator. The logical X operator takes you half the translation distance. And in this theory proposal, then this is a translationally invariant system under these discrete displacements. Yeah. So that doesn't really exist. It doesn't exist for 2 reasons. One is that you get errors. As you get errors, this oscillator gets moved around, jiggled around by the noise, yeah? And the system starts to broaden up. And the game of the error correction really is to make sure that as it broadens up, you can bring the system back to the origin before you get confusion over whether you're in the 0 state and the 1 state. So you say, can I put the states inside these boxes, and then can I detect, can I suck the system back towards its peak without identifying which of the boxes that these peaks are in? Yeah? So it's all about narrowing these Gaussians down. And it's about narrowing Gaussians for another reason, which is that we don't have infinite energy delta function peaks that go on forever. Yeah? So what we have is finite energy states. They tail off at higher energies, but nevertheless they provide this periodic structure, and you can see there's some small error due to the overlaps of these states now, but if that error is low enough, we can still use these to compute. Just to say this is the position basis, now we can look in the momentum basis, which is a Fourier transform, and these are periodic in both position and momentum. And to get these, we superpose squeeze states. We make a superposition of multiple squeeze states, and that's where we get this nice pattern in the quantum phase space. Okay, so how do we measure these states? What we do is very similar to the game I told you about before for laser cooling. But what you'll see is that, for instance, when I measure a logical operator, I measure this periodic oscillator, and you see it's got a much faster oscillation than before, because it has to identify whether I'm in the middle peak or I'm in the one next to it. So I want that the spin operator can tell me I'm here and not here. And if I measure the stabilizer operator, I have to oscillate even faster, okay, because I have to make sure that I'm plus for any of the peaks that I have in this distribution. So these are 2 chosen values of our displacement. Here's a scan of the displacement, and here's where we see a logical operator, and here's where we see a stabilizer operator. And now the problem of the overlap of the states comes in, because you see that this envelope is decaying down, and I'm not getting full information about this operator further out here, because my contrast is not 1 anymore. So how do we deal with that? Well, we look in the momentum picture, and we ask, why is the contrast not 1? And as I told you before, what we have is 2 copies of our original state getting pulled apart in momentum in order to identify information about the position. And so this leads to a loss of overlap. And what we've done, and one of our key contributions, if you like, in being able to do error correction, was actually to solve this problem. And the way we did it was to add a little bit of bias, which is now exactly the same type of operation, but proportional to the momentum. And what does this mean? It means that all of these peaks here now don't have an equal superposition of plus x and minus x, but they have an unbalanced superposition. And we've arranged it in such a way that this peak out here has a higher probability to get pushed back towards the origin than it does to get pushed out further into phase space. Yeah? While on the other side, then exactly the opposite happens. So when we apply now this measurement operation, what you see is much better overlap between the 2 copies of the state, and so we get a higher readout fidelity of our observables. So going from something like this, then what we see is that in theory, we could even have gone from a sort of 90% logical readout to something that's better than 99.9%. Yeah? In practice, we don't get that because we have a noisy copy of the quantum state, and that's dominating as at the moment. So that's the basis for doing quantum error correction. We go back to exactly the laser cooling sequence, but in a sense, what you see is that there's an extra pulse. The first pulse here is this conditioning, trying to make sure we can deal with our finite envelope of our states. The measurement pulse is what's in the middle, and that's extremely aggressive now because it's trying to find out about these stabilizer wave function, or stabilizer probabilities, and here's the correction pulse on the top. But nevertheless, all this is a unitary transformation that couples the oscillator to a spin. It gets reset, and then we do the same thing in the momentum basis. And what you see here is then starting from the ground state, all we do is we apply this laser cooling at some level, and we monitor what happens to our stabilizer observables. And you see we go from a ground state where the stabilizer is near 0 to a steady state where it's at about 80%. And that stays. This is the number of cycles here. And here in this plot, you see that we go up to 100 or so cycles, and we can go for 200 cycles. We stay within the manifold where this logical state lives. If we turn off the stabilization, we get a dramatic decay, and the thing instantly leaves the subspace. Yeah? So the stabilization is really keeping us inside the logical subspace. Of course, for a qubit, you want to know that your qubit lives. You want the information to stick around, right? That's a bit of a different problem. That's saying what's happening inside the qubit subspace while you're doing this. And here you see the results of such a scan. So these data here are for X and Z logical operators and Y logical operators, and this is what we happen when we don't stabilize the system. We don't do any error correction. But if we apply the error correction, what we see is we see a distinct extension of the logical coherence time, so there's more than a factor of 3 extension of logical coherence of this qubit. So error correction here is certainly extending the lifetime of a logical qubit encoded in this oscillator. So why is it that the green curve looks a bit worse than the red? What are our problems? Our problems at the moment are a little bit twofold. One is that our oscillator jitters in frequency, and that rotates this whole phase space backwards and forwards. Yeah? What that means is that any point that's further out in phase space is more affected, and that's why you see that, for instance, Y, which is this long diagonal, is more affected than the direct directions to the sides here. So we're sensitive to a number of things. We're working on that, but nevertheless, the first result is quite encouraging. So with that, let me give you a summary of what I've told you about so far. I've told you about this fact that we've been able to implement quantum error correction as well as laser cooling with a very simple cooling type scheme. Now what we're working on is a theory of multi-qubit gates, which actually has converged in a very nice way, where the theory tells us that we do an ideal gate, and we end up with a bunch of states that have been distorted. They all get broadened, they all get widened out. But the error correction then takes all of that out, and we end up with a perfect gate again. So it's very pretty. So there's some theory. We're building a new setup to actually work on this in a proper setup, and that's in a poster from Martin. And there are multiple other results from my group that I bring your attention. Something I think particularly striking for me, we just recently loaded in a new type of trap, in the sense it's a penning trap, but it's an extremely small penning trap, and that's quite an exciting moment for me in many regards. Yeah. So with that, then, I leave you with something that just should make any atomic physicist happy, I hope. Yeah? So tell me if you're not happy later, right? So somehow, of course, we're always trying to convey to the public what we do, atomic physics. And the reaction I always got when I stood next to the astronomer was, what I do is hard, and what the astronomer does is, like, beautiful. Yeah? And so I think the difference is in the perception of what we do, right? So can we make also atomic physics beautiful? We're trying. Since recently, you can go and see strings of barium atoms, individual atoms with your bare eye in the museum at Winterthur. They've been on display since January, actually. And you can even go and start playing with their quantum states, as the kids do. You can press them, they go dark, they come back at a random time sometime later. So I encourage you, if you're ever in Switzerland, to both come by our lab, but also go and see the atoms at Winterthur, and hopefully tell your friends about this too. Thank you very much.
Thanks, Jonathan, for this exciting news. I'm sure there are questions. There's one over there. Can you just go to the microphone? That makes it easier, so you're so close. Thank you.
Can you just say more about what an entangling gate looks like in this encoding? You said you teased some work right at the end.
Perfect, yeah, thanks. Okay, so I had the slide, I took it out because I thought I was going to hop on too long, yeah? So the basic deal is, if you have two ions and they both have an oscillator state, then they interact via a beam splitter interaction, fundamentally, yeah? That's not quite the gate that we would like to have. What we want is a phase shift that depends on the position of both these oscillators. And the beam splitter has also this momentum term that we don't want, yeah? But what we can do is that there's been nice work from NIST demonstrating squeezing of the quadratures of the oscillator. And what that means is if you sandwich such a beam splitter between some squeezing, then you can enhance the position term versus the momentum term. Yeah? What that means is that you can approximate actually very well the gate that you'd like to do, even with an oscillator, with an interaction which doesn't, well, conserves energy and thus has these two terms in parallel. Yeah. And my point was somehow that what that ends up doing, if you look at the marginals, is broadening. Before the gate, you get these nice spikes. After the gate, you get these broadened peaks. But this is exactly what I just told you we correct with the error correction. So somehow, in a very nice way, the error correction recovers us from something that comes in from performing the gate. Yeah? And that's been quite a pleasing feature for us. Yeah.
Are there more questions? Oh, Bill, sure. Sure, I forget it.
So I think you said this very clearly. You said that you, by doing this error correction, you extended by a factor of 3 the coherence of the encoded. You know what I'm going to ask.
Yep.
Did you extend the over the coherence of a single qubit, of a single physical qubit?
So not quite. So let me tell you about two physical qubits in our system. Yeah? One is the internal state of the atom, and actually that's quite bad compared to these ones. So our qubit that we're using internal to the atom is a couple of milliseconds, and we got up to 12 or so milliseconds for these coherences. And then you can go to the oscillator, and you can say, what's the simplest qubit I can implement in the oscillator? And it's probably, for our noise, superposition of the Fock state 0 and Fock state 1. And indeed, that shows better coherence by about a factor of 1.3 or so than what I'm showing for the corrected logical qubit. And then the fight becomes, how can you get to break even? And of course, that's on our target list, right? And a bit the challenge is that there's many sources of deterioration when you're doing all the error correction. What we find is we'll need to make the laser-ion interaction more linear. So we'll actually have to make bigger states in order to make the correction more precise. And coming with that will need to be a suppression of the dephasing noise of the oscillator. But there's a caveat, and I think one caveat I would say is that I'm not sure that I can do operations on this 0 and 1 superposition at the fidelities that I might be able to do them on the error-corrected qubit. Yeah? And if you look in trapped ions very often, the trapped ion system is a wonderful storer of a qubit. Yeah, actually, usually internal states that you specially choose, right? But the bad stuff's the gates. Yeah, I think we do the gates quite well, but still the bad stuff's the gate. And so somehow, if you get the right forum, I think you could probably be in a situation where you can protect your gates. And in fact, many of the gates that we have in the GKP are displacements. And if you make wrong displacements, then the correction should do a job for you. So we're looking forward to finding out if that's true for us. Yeah.
So, in my lifetime, are we ever going to see an immortal qubit? In the sense that it'll be.
So maybe I should just qualify what error correction does. It doesn't make an immortal qubit.
Exactly.
It makes a much improved qubit if you suppress errors well. And I think we're certainly getting to levels. In fact, there was a Google paper claiming that as they make their system bigger, the errors are going down just this week, if you like. I think we know how to do it. Yeah. So in the sense that will we see the break even coming soon? I think we will.
Yeah. But of course, what I mean by immortal is not that it's going to live forever. And note that I asked in my lifetime, I'm not going to live forever either. Okay. But is it going to live long enough to do the interesting calculations?
I think, yeah, that's a very interesting question. I think, if I look at what interesting calculations means, if I talk to sort of Matthias Treuer or something, they look extremely hard. And the reason is classical computers are amazing. Yeah, they can do just stunning things. And if you talk to the chemists, I talked to Marcus Raya at ETH, he probably says you're going to need 10,000 logical qubits or so, like perfect qubits, if you like, to do the sort of stuff that he would like a quantum computer to do in chemistry. And I can't predict when that scaling happens. So sorry to, maybe in my life, no.
Exactly.
Okay, on that note, can I just add one question because it struck me, you mentioned that just in passing on one of the final slides. What if you add now, say, a few more qubits to the same trap, which are all talking to the same bosonic modes? Would that work, that you can do each individual error correction on each individual one?
Yeah, I think, so I mean, even in a single qubit, we have 3 oscillators, right?
I know, yeah.
So we could try and do things in the 3 oscillators. I think of the single ion, for me, I would much rather do it, and that's why on Martin poster you would see that we try and do it with 2 ions and 3 ions and build it up like that, just because
Sure.
I have a purity thing going on there. But,
I certainly understand that, but I have a hard time understanding how this would work, say, for 10 ions in the same time.
okay, yeah, so but then I think probably if you think about surface codes, then this is why, if you like, I'm excited about these sort of ideas of
Yeah.
microtrap arrays, and I think that's been very hard to do with radio frequency traps, partly because there are many degrees of freedom you have to keep control of, and one really nice thing about the penning trap is you take a bunch of the hard control for ion traps and you stick it in a big magnet. So I have hopes for this. Yeah,
No,
let's see.
I do agree with you,
Yeah.
but the point is you see my difficulty understanding that with so many in the GKP code.
Yeah, but of course this would be a set of coupled oscillators.
Yes,
so
I
in
see-
a
I
sense,
understand
that's where
that.
I would come
Yeah.
from. Yeah, yeah.
Very good.
Yeah.
Are there more questions?
Yeah.
Can
This
you
is-
repeat the question?
Yeah, so the question is, if you wanted to embed this in a bigger code, sorry, I'm paraphrasing something. So I'd want to scale it up into a big code, then I have to worry that when I'm controlling a single system, the errors that I'm getting are not non-local errors that appear everywhere all over my code. This is somehow badly behaved in many of the codes we have. And I think one feature here is that, indeed, there could be a source of non-local error, which would be fluctuations in the trap frequency across the whole array. Yeah? But my feeling is that what you have is you've then got your local dissipation channel, which is kind of twirling the system locally because it's doing the error correction. You've got separate laser beams, making dissipation on a local site. And in a certain sense, this should, in a certain sense, collapse the long-range coherence. So my feeling is that that this is as well situated as a normal qubit system, if you like, to be robust in the sense of larger codes. Albeit that the codes I have in mind here would have to be something like a surface code, because the long-distance connections are difficult to do, probably. Yeah. Yeah. We can talk more afterwards. It's a complex topic. Yeah.
More questions?
There's one at the back.
In the back? I can't see you. Just go ahead.
Okay.
Please repeat the question.
Yeah, so the question was, is the reset playing a role in our preparation of states and in the recovery? Somehow, I mean, fundamentally, reset is the thing that is getting rid of entropy for us, yeah? So in order to end up with a pure state, I think we probably, or as close to a pure state as we do have to be getting rid of the entropy. Now, one of the initial ways in which we made these states was actually every time I write reset here, we made a measurement, yeah? But the problem was that what we had to do is we had to say, okay, we get that state, but conditional on the fact that all the measurements turned up being 0, yeah? And that's fine, but you waste a lot of your data. So we were very happy, if you like, to have a simple reset cycle, which then just looks like laser cooling, which now just pumps us into the right space. And that's, of course, much more efficient. We don't have to throw away any data at that point. Yeah.
Another question here? Do we have any questions online? No? If there are no questions, I would like to thank both speakers of the session, Klaus and Jonathan. Thank you very much for fantastic talks. And there's an announcement by the organizers.
All right. So this is your first lunchtime. Let me just give you a few pointers. If you want to read more about these, I'm kind of reading from the FAQ on our website, so you can look there. There is a little cafe resident in this hall. It's downstairs. It's called B Espresso Bar, and they can serve lunch across the 90 minutes, maybe 100 lunches, but we would easily overwhelm them, and it's not set up for large volumes. So I hope you all just leave the building and use that place as a last resort. And what you should essentially do is either walk west along Bloor Street, and once you get to Spadina, there's the beginnings of a whole strip of restaurants there. Or you can walk north to Cumberland. There's another cluster of restaurants around Cumberland. If you want to walk east, it's a little bit more of a walk, but you'll get to a place called Italy, and if you know that, you know it's a kind of upscale place. All Italians should avoid it, but anyone who's not Italian could go there and feel like they're in Italy. And if you want a grocery store, if you walk north on Avenue Road, there's a Whole Foods, also about 7 or 8 minutes walk. So please try to be back here for the next session. Let me remind all invited speakers and session chairs, for whenever your session is, please be up here and checking out your microphone, etc., 15 to 20 minutes before your session, whenever that is. Thank you, everyone. Enjoy lunch.